Say we are given a long, thick wire whose radius is r, and the current through it is I. Imagine this is a very long, infinitely long wire if you want. Our goal is to figure out the magnetic field everywhere in space. In this video, we'll focus on calculating the magnetic field outside the wire, and in the next video, we'll calculate the magnetic field inside the wire. So let's say we want to calculate the magnetic field at some distance r at this point. The question is, how do we do this? Well, we have seen two laws that help us calculate magnetic field due to current. One is called the Biot-Savart Law, and the other one is Ampere's circuital law. To use Biot-Savart, we have to take this entire conductor and divide it into tiny, tiny pieces and calculate the magnetic field due to each piece, because that's what Biot-Savart does. And then you have to add all of that up. And this is a very long conductor, meaning you have to integrate. This is going to be a nightmare. So not going to use Biot-Savart at all. But instead, we'll use Ampere's circuital law. What does this say? Just a quick refresher. It says choose a closed loop and walk along that loop and calculate this integral. And that should always equal mu naught times the current enclosed by the loop. And we've talked more about that in our previous videos on Ampere's circuital law. If you need a more refresher, feel free to go back and check that out. But at this point, you might say, hold on a second, Mahesh, even this has an integral, so what's the point? The point is, in certain situations, like this one, as we will see, we can choose very specific closed loops, very special closed loops. And if you do that, then this integral becomes super easy. Really, really easy. You don't even actually have to integrate. And then we can use this in a few steps. We can calculate what the magnitude, what the value of magnetic field is. That's the whole idea. So the question is, what closed loop should I choose over here? Well, before we do that, let's look at how the magnetic field looks like. Then I can think about what the closed loop would, loop should I choose? So what would the magnetic field look like over here? Well, we have seen before, in Earthstat's experiment, that magnetic field due to a wire will always be in concentric circles. So the magnetic field over here would be in a circular shape. So maybe somewhat like this, goes from behind, comes from here, and voila. And what's the direction of that field? Well, we use right-hand thumb rule. If the thumb points in the direction of the current, the encircling fingers will give us the direction of the field. And so our direction of the field would be this way. Let me get rid of the thumb. Now, let me show you what's special about this situation. Because every single point is at the same distance from the center, this is a circle, right? The magnetic field everywhere should have the same value. So the magnetic field over here, for example, it's tangential. So it's going to be in this direction. And if the value over here is 100, the magnetic field over here should also be 100 because the same distance. This is also a distance r, this is also a distance r. So over here, again, it's going to be tangent and maybe it's into the screen, but the value should stay the same, 100. Even here, the magnetic field value should stay the same. It's 100. And we're going to take the advantage of that. Because the magnetic field everywhere has the same value, if we choose a very specific closed loop, maybe B over that loop becomes a constant. And when I take that integral, that B can come out, and the integral can become very, very easy. So can you pause the video and think about what closed loop would you choose so that the integral would become easy? So pause and give it a try. It's okay if you're wrong, but it's just give it a shot. Try it. Okay, let me start by choosing a rectangle, just like that. So what will happen if I choose a rectangle? Can I use Ampere's law? Yes, Ampere's law works for any closed loop. I can walk along that rectangle, calculate that B dot dl integral, and I should get mu naught times the current enclosed. The problem is, because every point is not at the same distance from the center, that means the magnetic field everywhere over on this is not the same. And so now that integral becomes really, really complicated. Even the direction of the B and the direction of dl will also be like not the same. So calculating dot product will also be really complicated. So don't choose a rectangle. It's not a good loop. Ampere's law works, but it's not gonna help us. So to take advantage, maybe you have guessed it, let's choose a circular loop itself. And we call this an Amperian loop, whatever loop you are choosing. So let's choose a circular loop of the same radius r. Okay, here we go. Now notice as I walk around that loop, the magnetic field value everywhere is going to be the same. And so B can come out. But another interesting thing is, remember, we have to do a dot product. So we need to also know the direction of DL. And the direction of DL everywhere is in the same direction as B, because both are circles. So over here, DL is in this direction, same direction as B. Over here, DL is in same direction. Here also DL is in same direction. And so now the dot product also becomes easier to calculate because B and DL everywhere are in the same direction. So why don't you pause the video now and try yourself, okay, hopefully you're all pumped up, to try yourself what the left-hand side eventually simplifies to. So pause and give it a shot. Okay, let's do this. Let's do this together. So what happens when I simplify the left-hand side? Let's only consider on the left-hand side. B and DL are in the same direction. So what happens to B dot DL? Remember dot product? B dot DL would be, so B dot DL would be B DL cos theta, where theta is the angle between B and DL. But since the angle between B and DL is 0, cos 0 is 1, so this will just be B DL. So I'll just get magnitude of B times magnitude of DL. So I only have to worry about magnitudes now. I don't have to worry about direction anymore. Okay, what does that equal? Well, notice because the magnetic field is the same everywhere, the magnitude is all that matters now. The magnitude of the field is the same. I can pull this B outside. So this is a constant. This is a constant. So I can pull that B outside, the integral, and now I just have to do integral of DL. Now what is integral of DL? Well, logically, integrating DL means adding up all these pieces, tiny pieces of DL, adding all of them up, tiny lengths. What happens when you add all these tiny lengths? You get the total length, right? And do we know what the total length of this loop is? Yes, it's a circle. We know the total length of a circle. That's the circumference. Yay, so we don't have to do an integral, and that's what we meant. This is the circumference. This is circumference. And therefore, what happens? Let me write that down over here now. Let me write it over here, yeah. So what happens? We get B times, what's the circumference of the circle? It's 2 pi r. It is 2 pi times r. Which r? Small r or capital R? Well, we're taking circumference of this circle, right? That's why it's small r. So always think about what we are doing and you will not have any confusion. And that's our left-hand side. Like I promised, no integral at all. Okay, now let's look at the right-hand side. What is the right-hand side? We get mu naught times I enclosed. What is I enclosed? It is the current that is enclosed by the loop. And you can see that the entire current I is enclosed by the loop. But I'll do what Ampere suggests us. In general, Ampere tells us to attach a surface to it and then find what the current passing through that surface. And the way I imagine attaching a surface is, imagine I dip this entire loop in a soap solution, and then there will be a film attached. Let me draw that. There you go. And I enclosed is the current punching through that film. And you can now see that the entire current I is punching through that film. And so the entire current I would be our I enclosed. And now we can calculate what B is. Then let me write that over here. B equals mu naught I divide by, if we rearrange that, we get divide by 2 pi r. And what we see is that the magnetic field depends on the current, which makes sense. More current, more magnetic field. And we also see it's inversely proportional to the distance from the center. The farther I go, the magnetic field drops as 1 over r, which also sort of makes sense. What's interesting to see is that capital R is not in the picture at all, which means the thickness of the conductor doesn't matter. So whether this was a thick conductor or it was a thin wire, as long as the current punching through was the same, the magnetic field remains the same. Incredible, isn't it? Is this obvious? Not at all. But Ampere's law helps us understand that. Because in Ampere's law, we say that it doesn't matter how thick that current wire is, as long, all that matters is how much current is penetrating. And therefore, whether it's a thick wire or a thin wire, you get the same result. And finally, look at the number of steps involved. Not much, right? So you don't even have to, I don't even remember this equation. Whenever I have to think about the magnetic field due to long straight wires, I go back to Ampere's law and derive it.